Okay, so we're looking to solve exponential equations, and let me just quickly fix that one up there. So it's all about solving exponential equations. However, the really important bit here is that we're going to apply our understanding of quadratics and logarithms. Now that's really important because some of these, as you'll see with example A here, are really just straightforward testing your understanding of exponentials and indicial equations. But as you'll see, they progress to, can you recognise the quadratic? Can you use logs to solve in the final answer? Looking at it first and foremost, we can see here that we've got a base 4 and a base 16 and a base 256. And it's always going to be a lot easier if we can get a common base. So 4 to the 3x is fine, but the 16 here, we might change to be 4 squared to the power of 3 minus x. And the 256, well, 4 cubed is 64, and 4 to the power of 4 is 256. We can expand these brackets here. So 2 times 3 is 6, and 2 times negative x is minus 2x. So we've got 6 minus 2x, and that's still 4 to the 3x times 4 to the 6 minus 2x equals 4 to the 4. On the left-hand side here, we know that if we're ever multiplying indicials, that we just add the powers. So in the top here we have 3x minus 2x plus 6 equals 4 to the 4. And that is to say 4 to the x plus 6 equals 4 to the 4. Now we might read this as 4 to the something, let's call it x plus 6, is equal to 4 to the 4. So it seems quite simple here to equate powers. And by equating powers, we're going to say x plus 6 equals 4, which you might notice implies x equals negative 2 if we subtract 6 from both sides. So a simple process that we can think about here is first, let's get a common base. Then we can use our index laws to simplify. And if we've got a base to the power of something equals just that same base to a power of something, so if we've already got a common base, we've already simplified to one term on each side, we simply equate powers. Now, that's all well and good when we're looking at a question up here that can just be solved simply by index laws. But now we look at something with a 7 and a 3, and we notice that we cannot possibly get a common base. So these we might think like solving brute force. If I carry the 3 over, I'll get 7x minus 3 equals 3. Now if I log base 7 both sides, so we might just rub out that 3 and say that we're going to do log base 7 both sides, we can see here that we've got the opportunity to resolve x minus 3. So x minus 3 times log 7 of 7 equals log 7 of 3. Now we might notice that log 7 of 7 is just 1, and so x equals log 7 of 3 plus 3. That's just a number, so that's solved. The big difference to note with questions like this, where they don't have a common base, is that it's really quite important we know that we can use logs to solve them. So we might just flag it here, where there's no common base use logs. Looking at problems such as part C here, this is the part in the learning intention which we reference quadratics. You may remember from 1-2 methods that these types of indicial equations, they look like trinomials, and so making a simple substitution, we can create a quadratic trinomial. So the first thing we might recognise is that this middle term here is 3 to the power of x. So let's let a equal 3 to the x. The other thing which we might need to recognise is that 3 to the 2x can be written as 3 to the x squared, because if I multiplied that down, it would equal 3 to the 2x. So if I replace a with 3 to the x, we'll note we have a squared minus 9 times a plus 14 equals 0. We also know that the factors of 14 that add up to -9 are -7 and -2. So let's now rewrite this as a minus 7, a minus 2 equals 0. And if we solve, we know that a equals 7 by null factor law and a equals 2. It's important at this point to resubstitute, because we aren't asked to solve for a, we're being asked to solve for x. And we note that up here, we let a equal 3 to the x. So 3 to the x equals 7, and 3 to the x equals 2, which we can solve. X equals, if we log 3 both sides, and x equals log 3, 2 if we log both sides. These are just numbers, and so our answer can be left as such. Part D is an interesting problem because there are a few ways that we could do this. It's important when we see something like this, which is not clearly a trinomial and not clearly everything's got a common base. The 4 may have a common base too, but the 3 may not. This is a question where we might have to use a mix of our skills to solve. So we can start, I guess one way to think about this is a bit like brute force method. If we just expand everything and try to solve as best we can, we might find that we can get somewhere. So if I multiply 2 times 2 to the x minus 1, it's a bit like saying 2 to the 1 times 2 to the x minus 1, which we know if we just add x minus 1 and 1, we end up with 2 to the x. And then 2 minus 3 is going to be minus 6, and plus 4 equals 0. So now we end up with 2 to the x minus 2 equals 0. If we bring the 2 over, we can see that 2 to the x is equal to 2 to the 1. And if we equate powers as we did in part A, we note x equals 1. Now this isn't the only way to solve a problem like this, but certainly feels like the most efficient. So it's good to know that we can mix and match a few different skills, and it's really important, as I think many people will forget what we did here, which was that 2 times 2 to the something, we just add powers like we normally would.